So let's look at how strong a solenoid is. So aim is calculating or calculation of magnetic field inside a long straight ideal solenoid. So the funda is quite simple. We'll take a solenoid and we have the current going out over here. That is, you can imagine it's, just a second, it's helical structure, right? So we are viewing from the top. So this is your top view. So current is coming to us. Here current is going in. So the magnetic field will be, this will be north and this will be south. How do we find this? All this has to be known. Yeah. How do you find this? Correct. Using our right hand rule. So we'll just draw few arrows. Okay. Now we are looking at Ampere's, making use of Ampere's circuit law. So for that we need an Ampere loop. So it's just a set of lines. In this case, it's convenient for us to take a rectangle enclosing the entire solenoid. That's our rectangle, and next is we have to decide on the right. Just a minute. This is your Ampere's loop. Now, next thing that we need to decide on is the direction of integration. Think about it. How should it be? What's more convenient? Should the arrow go up or down? That's what you guys have to decide. Again, make use of right hand rule. So your curling of the finger should be in the direction of the integration. So is this convenient or should I take anything else? This is kind of convenient because the magnetic field line and this will be, to the up in this case, up the screen, and the current enclosed is down and our right hand rule also points down. So the current direction and our thumb direction is the same. So taking our RHS I enclosed to be positive. So this is convenient. Now we have to integrate all around. So integration along this path, say I'll call it as path 1. It will be same. Path 2, it will be same throughout the path 2. Path 3 will be same and path 4 will be same, right? With respect to within that space. So once we have this, then apply our Ampere circuit law, take each path, apply it. So that will give us our LHS. RHS, it's about how much of current is going through. For that, we need to use these variables over here, written over here, and we are done. As simple as that. So let's start the derivation. So we consider an ideal solenoid. In ideal solenoid, we don't see actually, ideally, of course, there is zero magnetic field outside the solenoid. That's why you're taking ideal solenoid. So the length is L, number of turns within the space is N. The current through the entire circuit is I. Number of turns per unit length, this we need, we're calling it a small n. So that will be N by L. N by L. So we need to consider a rectangular Ampere's loop that runs inside and outside of solenoid, covering the entire length of the solenoid, as shown in the figure. As shown in figure. That figure you guys have to draw this. Draw it over here. Okay. Next. Next, what should we do? Next step is to talk about as per Ampere's law. Applying Ampere's law. So we have integration of PdL, which is equal to mu naught I enclosed. So we have path 1 BdL plus, right? This has to, we have to cover the entire path. That's what the LHS tell. And path 3 PDL plus path 4 BDL. Let's concentrate on LHS first. So let's only take LHS. Agree, guys. So the entire circular path or entire path that we have to integrate, that we have divided into 4 parts. Agree? So next we have path, the angle, and cos of theta. Because here we have, sorry, I kind of missed it. This has to be all dot producted. So this is dot, dot, dot product, dot product, dot product, dot product. Okay. So dot product leads to cos theta. Now let's go to this figure. What is the angle for path 1? What is the angle between which one? B and DL. B is the magnetic field. DL is any point you take. That is your DL. So it's tangential and in the path of the imaginary. This is your path of integration or direction of integration. So angle between path 1 and the magnetic field is what? Path 1 is correct 0. So this will be 1. Next path 2. Path 2 will be, you can see over here it is 90 degree. So this will be 0. Path 3. Path 3 there is none. So let's skip that for now. Path 4. The angle between them is 90 degree. And so this is 0. Okay. Then what about path 3? We missed out path 3. Path 3 is this. Well, there is no field per se. So as the exterior field is almost equal to 0 for an ideal solenoid, the entire LHS turns out to be integration of PDL into 1 path 1. That's it. Okay, so let's move on to 1. So let's go back to 1. Substituting in 1, what do we end up with? We have, see, integration of entire length of DL in path 1. What does it lead to? This entire length is what? This entire length is, if I add all of this, what will it lead to? Length L, that's the length of the solenoid. So we are taken for the entire length. So when I integrate DL, because B is constant, right? B is constant, that's what we have written over here. Because solenoid is ideal, B is in the interior space is uniform and parallel to the axis. And the magnetic field line is in the exterior is considered to be negligible. So all in all, we have this to be BL, which is equal to mu naught Ni. So we are done, almost done. That's actually an answer also, but we need to express in terms of density, turn density. How many turns are there per unit length? So that will be equal to mu naught NLI. So NL is nothing but N, small n, right? That's the turn density, is it not? That's how we represent it. Initially we did that. Here N by L is turn per unit length. And so that's your final expression. So what can you conclude? If I increase, conclusion, B increases if 1s N increases 2 is if I increases. And it's constant throughout the throughout the solenoid, inside the solenoid. Right, guys? Okay. Finally, we have the graph. So we are looking at magnetic field strength, sorry, not E, B, and the distance. Say this is your end of the solenoid. So basically it would be so. So the magnetic field, the strength will be same throughout. But at the end of solenoid, you don't have this derivation per se, right? But I want to show it to you guys. It will become half of it. So say this is B by 2. It'll drop by half. It'll drop by half. So that all in all, this is what we're looking at. So this is again end of solenoid. So that's the graph if they ask for it. If not, here till here is your derivation. So what is that we are doing? We are looking at solenoid's strength, magnetic strength inside. We're taking up an ideal solenoid. So inside it is there, magnetic strength or magnetic fields are running. Outside it's not. Next, we are making use of Ampere circuit law. So for that, we need to consider Ampere's loop. So we have to consider the direction of integration in such a way that it will overall give us the entire integration with no hindrance. Whatever you take, whatever you do, you will end up with the same answer. But if you take it in a very smart way, then all of them will be positive, so there's no confusion. So we took it in clockwise because here inside the magnetic field line and the direction of integration matches and the direction of the current also matches with our right hand rule. If you understand this, pretty much everything else is quite simple. So we have to consider a solenoid with length L, number of turns is N, current is I, so on and so forth. Next, when we apply Ampere's law, we take up the LHS. RHS is quite simple. We just have to take up the LHS, understand that it is integration of the entire path. So start with path 1 and end with path 4. So all of this are dot product. So we have to figure out the angle. Angle, it's very simple. 1 and magnetic field lines are in the same direction, while path 4 and the magnetic field lines are making an angle of 90 degree, as you can see clearly. Okay, so you can clearly see this is 90 degree. This also is 90 degree. These are in the same line, same direction. There's no magnetic field over here, so we can ignore that. So all in all, we have, when we substitute back this to 1, we have BL mu naught Ni. Okay, so of course, substituting this and substituting that there is no exterior field. And so only one term will be left out, that is through the path 1. Since B is constant, integration of dl will be L. We're just adding up the entire length of dl, so that is nothing but L. Right? I hope the integration is very clear. Basically, we are adding up the entire length of L. So adding up the entire length of L is L. Adding up all the small bit of lengths in a 10 centimeter line is 10 centimeter. Right? Does it make sense? Now we have to express in terms of turn density and all of that. So that's it. Okay, now it's pausing and having a look time.